The screen opens on an endless starfield, pinpricks of light in velvet black. A low, resonant voice begins. We have been listening for a century, and the universe has spoken to us in riddles. From the static of radio telescopes to the flash of a millisecond pulse, humanity has recorded transmissions that refuse to be tamed by explanation. Some last a heartbeat, some repeat in impossible patterns. Some were finally traced back to ordinary machines, and others remain stubbornly alien. Tonight we will walk through the most mysterious signals ever detected in space. From the famous WOW signal to the repeating fury of FRB 121102. And we'll ask the question that lingers after every discovery. What exactly is trying to tell us something? Make sure to subscribe, because the sky is whispering, and these whispers might change how we think about our place in the cosmos. The wonder of listening. For more than a century, we have built instruments to listen to the heavens. Radio telescopes, parabolic dishes, and arrays turn the invisible radio sky into sound. In those sounds are natural choirs, pulsars like metronomes, the hiss of cosmic microwave background, the roar of quasars. But occasionally, among the expected notes, an odd tone appears, an event that looks nothing like the orchestra we know. These are the anomalies, bright single pulses that decay too fast, narrow band spikes that suggest focused transmissions, repeating sources that flare in complex patterns. Some are explained quickly, some take decades. A few never yield their secret. In this narrative, we'll treat each signal like a case file. Discovery, how it was recorded, what scientists did next, the leading explanations, and why it still matters. The signal that wouldn't repeat. On a late summer night in 1977, at Ohio State University's Big Ear radio telescope, an automated computer printout captured a curious cluster of characters. 6EQUJ, 5 astronomer Jerry Eamon circled it and wrote, "WOW" in the margin, and the name stuck. The WOW signal was a narrowband radio burst at about 1420 MHz, a frequency associated with hydrogen, long imagined as a likely band for interstellar communication. It was strong, localized, and unlike the broad, noisy signatures of natural sources. But then, silence. Repeat observations of the same patch of sky turned up nothing. No second pulse, no steady beacon. The WOW signal was a single bright event, lasting 72 seconds, that vanished when the telescope's beam moved on. Over the decades, astronomers have tried to reconstruct it, checking records, scanning the same coordinates, and searching for any pattern in the data. Some suggested terrestrial interference, perhaps a passing aircraft or an earthly transmitter, though the frequency is protected, and such interference should have shown up elsewhere. Others floated astrophysical possibilities, a previously unknown kind of transient, or a natural maser. Still others allowed their imaginations to drift toward deliberate signalling. The core problem remains simple and brutal. Science runs on repeatability, and the WOW signal never repeated. It remains an unsolved ghost in the archives, a single flash that still raises the hair on the back of the neck. The Lorimer burst. The first FRB we didn't understand. In 2007, a discovery shattered radio astronomy's assumptions. The Lorimer burst. While sifting archival data from the Parkes Radio Telescope in Australia, astronomers Duncan Lorimer and his student found a single, extremely bright millisecond radio pulse that dispersed in frequency in the way that distant impulses do when they travel through interstellar plasma. The dispersion measure suggested the burst came from far beyond our galaxy. It was far too powerful to be a simple local source. The Lorimer burst was the first hint that a whole new class of cosmic explosions existed. Brief, bright and energetic radio flashes whose origin was unknown. At first, the community worried that these were artifacts, glitches in instrumentation, or local radio interference. Then more pulses were found in archival data. A new class of object was born, fast radio bursts, or FRBs. The Lorimer burst forced astronomers to confront a puzzle. What mechanism could produce so much radio energy in a millisecond? The discovery spurred new searches, new telescopes, and an entire field devoted to these fleeting enigmas. Fast radio bursts. A cosmic menagerie. FRBs are the wild cards of the radio sky, milliseconds long, yet luminous enough to outshine galaxies in radio energy. They arrive with dispersion patterns showing they traverse huge columns of plasma, implying extragalactic distances. They come in two broad flavours, apparently one-off bursts and repeaters. Initially, most FRBs seemed singular, a single bright blip and never again. That made localization and follow-up nearly impossible. But then the universe surprised us. Some FRBs repeat. Among them, one stands above all others for mystery and importance. FRB 121102. Understanding FRBs requires patient, high-cadence observing. It requires arrays with precise timing and localization capability. And it requires a new kind of astrophysical imagination. Are FRBs cataclysmic events like neutron star mergers, which cannot repeat? Or are they emissions from extreme magnetospheres, capable of multiple outbursts? The answer, as with many things in astronomy, is likely plural. FRBs may be a menagerie of phenomena, not a single type of object. Even so, the very existence of these bursts, particularly the repeaters, forces us to re-examine the extremes of cosmic physics. FRB 121102. The repeater that challenged everything. First seen in 2012 in archival data and formally announced in 2014, FRB 121102 changed everything by refusing to be a one-off. Multiple powerful bursts were detected from the same sky location, and careful interferometry pinned that source to a small dwarf galaxy more than 3 billion light-years away. Even more puzzling, FRB 121102 sits within a tiny but persistent radio source, a nebula or compact region that emits continuously, and its bursts show extreme rotation measures, implying propagation through an intense magnetic environment. The repetition forced theorists to abandon purely cataclysmic explanations for at least some FRBs. Instead, models invoking young, highly magnetized neutron stars, Magnetars, embedded in dense nebulae, or even accreting black holes in turbulent environments, took center stage. But each idea has complications. For FRB 121102 to produce such burst energies repeatedly, the engine must be both powerful and long-lived, and the surrounding medium must be dense and magnetized enough to explain the observed rotation. Observers found complex substructure in individual bursts, microsecond timing features, and spectral flickering, clues pointing to local plasma lensing or dynamic magnetospheric processes. FRB 121102 became a laboratory for extreme physics, a single object that demanded new theories of how compact objects behave when pushed to their limits. FRB 180916, periodicity, and patterns in the chaos. In 2019 and 2020, more remarkable behaviours emerged. Some repeaters showed activity windows, phases in which bursts were more likely. FRB 180916 exhibited a roughly 16-day periodicity. 4 days of intense bursting followed by about 12 days of quiet. That rhythm suggested orbital motion, or precession, or perhaps a rotating engine modulated by the environment. Periodicity gave astronomers a new handle to plan observations and to probe physical mechanisms. Periods are clues. They point towards systems with clocks, orbital companions, magnetar spin, and precession, or a beam swept by rotation. The discovery of periodic windows turned FRB science from blind stares into scheduled hunts, enabling detailed monitoring that revealed changes in spectral behaviour and polarisation across cycles. Each new pattern deepened the puzzle. FRBs can be coherent, structured, and sometimes rhythmic, but the underlying engines remain under debate. Perytons, microwaves, and the humbling of astronomy. Not every mysterious signal turns out to be cosmic. In the mid-2000s, Parkes radio telescope operators recorded enigmatic bursts they named Perytons, signals that looked surprisingly like FRBs, but repeated across multiple beams as if they were local. For years, Perytons baffled researchers. The pattern was inconsistent with celestial point sources. The mystery solved itself in a very human way. The culprit was microwaves. Staff opening microwave oven doors while the ovens were running created broadband emission that the telescope detected as Perytons. The revelation was humbling, but instructive. Not everything that looks extraterrestrial is. Rigour, diligence, and the cold light of instrument checks are as important as imagination. The Peryton episode taught the field to discriminate between terrestrial contamination and genuine cosmic phenomena. And it reinforced the scientific protocol of skepticism. The WOW signal versus FRBs. Different beasts. It's important to keep the WOW signal and FRBs distinct. The WOW signal was a narrowband emission at the hydrogen line frequency. FRBs are broadband, highly dispersed millisecond flashes. The WOW signal's allure has always been its apparent targeting of a frequency of interest to communicators. FRBs, by contrast, look like violent physical events. Both raise questions about uniqueness, repeatability, and origin, but they invite different explanations and different search strategies. Where the WOW signal tempts SETI-style thinking about intentional communication, FRBs are forcing astrophysicists to expand models of energetic transient events. Both remind us of the sky's capacity to surprise. FRB 200428. A galactic clue. Then in 2020, a watershed moment occurred, the detection of a radio burst from within our own galaxy associated with a known magnetar, SGR 1935+2154. The event, labelled FRB 200428 by some catalogues, was far less luminous than extragalactic FRBs, but shared properties on a scaled level. It suggested that at least some FRBs, especially the repeating kind, could be produced by magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. The galactic magnetar burst gave theorists a laboratory they could study closely, connecting magnetospheric physics and crustal activity to the production of coherent radio emission. Yet it also complicated the mystery. The energies of cosmological FRBs are 1,000,000 times higher than FRB 200428, so either extragalactic magnetars operate in regimes we don't fully understand, or a range of engines produce FRB-like bursts. The 2020 detection narrowed the field of theories but did not solve the riddle completely. Tabby's star, solar anomalies, and other odd lights. While radio astronomers wrestled with FRBs and the WOW signal, optical and multi-wavelength astronomers encountered their own mysteries. One famous case is KIC 8462852, better known as Tabby's star, which exhibited bizarre irregular dimming that sparked speculations from dust clouds to swarms of megastructures. That idea temporarily laboured in public imagination, but careful work pointed toward dust and natural processes. The lesson is parallel. A strange light curve does not equal alien engineering, but it does deserve intense scrutiny. Similarly, odd radio and optical events tied to the sun, pulsars and flare stars continue to reveal unknown physics. The universe is a laboratory of extremes, and the more we look, the more extremes we find. Why these signals matter? More than mystery. Each unexplained transmission is more than a curiosity. They are data points that force revision of theory and design of new instruments. The WOW signal taught us the value of continuous sky monitoring and the heartbreak of non-repeatability. The Lorimer burst and subsequent FRBs inspired new telescopes, from CHIME in Canada to ASKAP in Australia, built specifically to catch our fastest radio fireworks. The repeating FRBs demanded rapid localization techniques and multi-wavelength follow-up, forging collaboration between radio, optical, X-ray, and gamma observatories. Even Perytons changed how observatories manage radio frequency interference, improving the rigor of transient detection. Collectively, these anomalies have pushed astronomy into a golden age of time-domain exploration, a field that studies the universe not just in space, but in the beat of events across time. Theories, from magnetars to extraterrestrial civilizations. Over the years, a parade of hypotheses has vied to explain these signals. For fast radio bursts, magnetars and neutron star activity are leading contenders, offering mechanisms for powerful, coherent radio emission. Models include magnetospheric reconnection, crust cracking, and relativistic shocks that produce maser emission. Other astrophysical ideas invoke black hole accretion, collisions of compact objects, or exotic phenomena like cosmic string cusps. SETI thinkers have intermittently proposed deliberate signaling or leakage from advanced civilizations, especially when considering narrowband or highly structured signals like the WOW signal. But the scientific method demands conservative inference. Extraordinary claims require extraordinary evidence. So far, while some signals tantalize, none provide the smoking gun for extraterrestrial intelligence. The most parsimonious explanations remain rooted in extreme, but natural, astrophysical processes. How we look now. New telescopes, new strategies. The search for answers has driven new capabilities. Wide-field instruments like CHIME monitor large swaths of sky every day, capturing thousands of FRBs and enabling statistical studies. Interferometers like ASKAP and the Very Large Array provide localization to arc-second precision, allowing identification of host galaxies. Optical telescopes and X-ray satellites perform quick follow-ups to see if a radio flash has an afterglow. Machine learning sorts terabytes of data to spot real events from noise. The strategy has shifted from passive listening to active hunting, scheduling observations to catch periodic repeaters, coordinating global networks for immediate follow-up, and building archives for retrospective discovery. Each improvement increases the chance that a new, repeatable signal will provide a clear physical context, turning mystery into mechanism. Where mystery meets humility. Lessons from false alarms. History reminds us to be humble. The Peryton fiasco, the transient optical oddities, even early misclassified pulsars show that the path from anomaly to understanding is littered with human error, instrument quirks and terrestrial contamination. But false leads are not failures. They refine methodology, force stricter controls, and improve the robustness of discovery. The discipline of ruling out every plausible terrestrial cause before embracing the cosmic answer is the foundation of reliable science. Each time we defeat a false alarm, we sharpen our tools for the real puzzles that remain. What would proof look like? Proof of extraterrestrial signaling would be unmistakable. A narrowband, structured transmission repeated multiple times, encoding patterns that defy natural origin, accompanied ideally by modulation across wavelengths or a directed localized beacon. For astrophysical phenomena, proof is different. Localization to a host galaxy, identification of a counterpart at other wavelengths, and models that can reproduce the energetics and observed structure. Both roads demand repeatability and context. That is why FRB localization was a watershed. Once we could tie an FRB to a galaxy and a persistent source, the mystery shifted from "is this real?" to "what is the engine?" For the WOW signal, its refusal to repeat is the obstacle that keeps it an enigma. The human side. Why we care. Why do these whispers matter to us? At a fundamental level, they challenge our expectations about the universe. We grew up imagining stars as constant and quiet, and yet the cosmos is a dynamic theatre of births, deaths, and electromagnetic fireworks. Mysterious signals push technology forward, unite international teams, and inspire the public imagination. They force us to confront our assumptions and to invent new physics when necessary. Even when a signal turns out to be a forgotten microwave oven, the process of discovery and correction strengthens science. That is a feature, not a bug. The next decade. A promise of discovery. The coming years promise transformation. As arrays collect thousands more FRBs, as localization becomes routine, and as multi-wavelength follow-up accelerates, patterns will emerge. We will learn whether FRBs are a single class of object or a collection of distinct phenomena. We will likely identify engines in concrete astrophysical settings, and perhaps at least one surprising signal will force a rethinking of known physics. SETI searches will continue, leveraging the same instruments and algorithms that count FRBs, probing both narrowband and broadband signatures. The sky will keep talking. Our job is to listen better. Conclusion. The unfinished symphony. The universe speaks in many voices. The steady tick of pulsars, the long sigh of radio galaxies, and the sudden cry of FRBs. Among those voices are puzzles that refuse to be solved. The WOW signal remains a lonely outlier. The Lorimer burst was a herald of a new class. FRB 121102 taught us that repetition can be the key to unlocking physics, and Perytons taught us humility. Each case is a stanza in an unfinished symphony, and we are still learning the score. As we sharpen our instruments and extend our reach, we may yet translate these whispers into comprehension. Or we may discover new mysteries that dwarf the ones we have now. Either way, these signals remind us that the sky is not a silent vault. It is a conversation, sometimes baffling, always instructive, and forever worth listening to. If this story stirred your curiosity, subscribe and stay with us, because the next strange pulse might come tonight. And when it does, we must be ready to hear what the universe is trying to tell us.